Okay, 8.4. So far we've dealt with transition matrices, but we haven't added any people or objects into the existing population at all, or had any be removed in any way. We are now going to look at it in terms of restocking or culling. So adding in or taking away things from the population. So they operate very similarly, but we just have to do a few little extra things on the end to show this restocking or culling. Okay, so here we've got our initial state matrix. We've got transition state given. So we're going transition times our initial state gives us where they move to in the next iteration. Okay. Now, it is very unlikely that, for example, in the workforce, you are going to have the same number of people remain in that organization forever with no one leaving or joining. It just doesn't reflect real life. So we have to show this in our matrix calculations. So we know that every year 24 people enter the industry to work as casual. So we've got those people reflected here. And we've got 35 permanent employees leave the industry. So negative 35. So we're showing that they are leaving by using the negative operation. That's the culling effect. And those 35 people to our calculation. So we've still got transition matrix, initial state, and then we do this adding on our culling and restocking here. So we still do our multiplication first. So BODMAS still applies. So multiplication, and then we're going to do that restocking and culling on the end to actually show the state of our population. All right. Can you see that now when we add those elements, it no longer is the same value because we've moved where people are, either we've got more people in or more people have moved out. So initially we had 1,640 people in our sort of mix. We now have 1,629 people in the mix. Sometimes too, we actually use the years. So something to note is that this might not be that it's 2025 iterations. It's actually the year 2025. So just keep that in mind when you're working through with restocking and culling. It does make it easier to work with because you know where you're at. So the recurrence relation, remember there is going to be two parts to the recurrence relation. So we have our SO, which is our initial state. We have our comma. We have the next number of in our sequence is equal to our transition matrix multiplied by our previous value plus our B. Now B is that restocking and culling. So it can have both positive elements and negative elements, but it must be the same order as S of n. Okay, otherwise, remember, we can't do that addition. There is no shortcut rule for restocking culling. The recurrence relation always has to be used to answer these questions. So you can't actually jump to a period in time. You are going to have to work through each iteration every year. So please keep that in mind. Okay, let's have a look. We've got a karate school and it regularly assesses its students as they progress through the 3 belts. After each assessment, students are classified as white belt, orange belt, blue belt, or they've left. Students cannot be assessed at a belt level lower than their current belt in the recurrence relationship shown. So initial state is SO. It's the number of students at each belt level immediately before the first assessment of the year. The transition matrix T has the percentage of students who are expected to change their belt or leave the school after each assessment. And the matrix J contains the number of students who will join the karate school after each assessment. Okay, so we started with 80 students who had a white belt, 60 students who had an orange, 40 had a blue belt, and none had left the school. So we've got none, that are showing as being already outside the school. And we've got our occurrence relationship. Can you see that we've got, like, this is the two parts, initial state and how we find the next number in our sequence. Recurrence relation, two parts. So before the assessment, and after the assessment. So they expect 25% who were white belt to go to white belt. They expect 45% who were white belt to move to orange belt. They expect 65% who were orange belt to stay orange belt. Can you see that no one's jumping? No one's going from white belt, like up more than one belt. They can only assess to the next level. So that's why we haven't got white belt moving to blue belt. White belt and leaving, we've got 30% who were a white belt who are going to leave the assessment. Okay. If they left, then they left. If they were a blue belt, we've got 70% staying at a blue belt. If we've got a blue belt, then 30% are going to leave. This is who is joining after that first assessment. So 16 are going to join at white belt. We've got 3 joining who are orange belt, 4 joining who are blue belt, and none joining who are leaving, if that makes sense. Okay, so we're going to go through our first iteration. So we take our transition matrix. So after one assessment, transition matrix multiplied by our initial state, and then we're going to add on that culling and restocking. So can you see here? So we end up with 36 at a white belt, 78 at an orange, 44 at a blue belt, and 45 have left. So after the first assessment, there are 36 students with a white belt after the first assessment. Okay, so now we want to find the blue belt after the second assessment. So we need to use the S of 1. So this is now our S of 1. Remember, we're not going right back because we want to do after the second assessment. So we're using this value. So we had to do our first assessment, was a new matrix of where our students are sitting with their belts. Then we're going to go to our second assessment using our first assessment. So we know now we've got 50 students who have a blue belt.